let me first write it down. Polynomial size monotone formula for the majority function. Okay. So, let us try to understand what is this. So, we know what the majority function is, right. So, it is a threshold function where if the number of ones in a string, in an n bit string, is greater than or equal to n by 2, then the function outputs 1, otherwise it outputs 0. Now, what can we say about a circuit or a formula size computing majority? Okay. So, we can of course construct circuits, we can of course construct polynomial size circuits for majority. In fact, very easily one can construct a log n depth circuit size for majority, and the same can done the same can be done with a formula as well. Okay. So, for the majority function one can construct a formula, a log n depth formula which solves majority, right. But if you look at the majority function has a special property. Okay. So, it is what is called as a monotone function. Okay. So, formally I will define what a monotone function is later on, I mean I do not need it today, but intuitively let me give you the idea. So, a function is said to be monotone, okay, if let us say on some input, okay, some string, the function takes a value 1. Now, if for all other strings, okay, so let us say the function takes a value 1 on some string x, for all other strings y such that y is obtained from x by changing a 0 of x to a 1, okay, the function has to take a value 1 as well. Okay. And that is very obvious for the majority function, right. So, if it takes if you have a string which has n by 2 ones, then the function takes a value 1, and if I change any 0 to a 1 in this string, the number of ones is only increasing, and majority of course will take a value 1. So, in some sense if I look at let us say a hierarchy of these strings, so there are 2 to the power n bit strings. If I look at the hierarchy of these strings, where this hierarchy is constructed by looking at how many ones are present in that string, then the function value also monotonically increases. So, it takes once it takes a 1, it keeps on continuing taking 1. So, that is the intuitive meaning of a monotone function. Now, what do we mean by monotone formula? Okay. So, a monotone formula is a formula, can you guess what kind of a formula would be monotone? Okay. So, intuitively I want the formula to have something like this, that once it gets a value 1, that kind of should percolate upwards. So, what do you think would be the definition for a formula to be monotone? Okay, so let me tell you. So, a formula is monotone if it does not have any NOT gates. Okay, so once I have a 1, I mean there is no way to flip it back to a 0. Okay, so a formula, any formula is said to be monotone, and in fact the same definition is used for circuits as well. It is said to be monotone if there are no NOT gates. Okay, so we will look at this basis M2. Which consists of only OR and AND. So, 2 because it is the 2 input gate, 2 input OR gate and the 2 input AND gate. Okay. So, the point is we want to construct. So, now we have seen formula over the De Morgan's basis, we have seen formula over B2 basis. Now, we will look at formula computing majority over this M2 basis, that is no NOT gate. And okay, so the first question that arises is that can we even compute majority over this basis? It is not even clear. Okay. So, there is something called a complete basis. So, a complete basis is a basis over which any function can be computed. So, this is clearly not a complete basis, because you can clearly define some functions which are not computable. De Morgan's basis is a complete basis, B2 is a complete basis. This is not a complete basis. Okay. But the question is that well, it may not be complete, but can I ask the question that can it compute certain functions, more specifically can it compute certain monotone functions. So, I just argued that majority is a monotone function. So, the obvious question is, can this basis compute the majority function? The answer is yes, majority, it can be shown that majority can be computed by this over this basis M2. Next question is that, well, if it can compute majority over M2, what is the smallest sized formula over this basis that can compute majority? That is the question that we are going to focus for the rest of today's lecture. Okay. Now, when we say polynomial, okay, so we want we will basically be giving a formula which is not just polynomial, but even the depth is bounded by log n. Okay. So, it is like a one direction is obvious, like if the depth is bounded by log n, then the size has to be polynomial. But if the size is polynomial, it is not necessary that the depth is bounded by log n. So, we will actually be proving a stronger result, that will prove a monotone formula for majority whose depth is bounded by log n. Now, there have been several works on this problem, and people have given formula whose sizes have been quite large. Okay, so, they have been polynomial, but using something called sorting networks, it was shown to have polynomial size formula. But unfortunately, those polynomials were huge. I mean, the exponent of that polynomial, the exponent of n was like very large. I mean, it is like impractical to even apply. So, what Valiant showed, okay, so this is the theorem that we are going to prove in, I think in 83, if I am not mistaken, I do not have the date here, 84, okay, that L M2 of majority is n to the power 5.3. Okay. So, yeah, I will just write order over here, maybe some constants before it, but it is roughly n to the power 5.3. And actually, so this is just the size of the formula, but as I said, we will show a stronger bound. So, we will show there exists a formula of depth at most 5.3 log n. There exists a monotone formula, or okay, formula of depth over M2 that computes majority. Okay. So, any questions? So, let me quickly even recall what the majority function is. So, majority of x1 to xn is equal to 1 if sigma xi is greater than n by 2, it is equal to 0 otherwise. Okay. So, one more, so before proceeding, one more point about this construction, or well, this is actually not a construction, but about this argument is that this is a probabilistic argument. Okay. So, what Valiant showed, he actually did not construct an explicit formula for majority, but he showed using a probabilistic argument that there exists a formula having these properties which computes majority. Okay. So, that is kind of like a non-constructive proof, but it is still a proof. Okay. So, how do we prove this? So, to prove this, so yeah, so to prove this we will first construct a random formula. Okay. So, construct a formula as follows. So, first what we do is that construct a complete binary tree of depth 5.3 log n as follows. Okay. So, what we do is that we have a, let us say, an OR gate at the top, then its children will both be AND gates, and essentially what we will do is we will have this complete binary tree, and alternatingly in alternate layers we will put AND and OR gates. Okay. So, let us say at the first layer we have OR, then we will have AND, then again we will have ORs and so on, and actually the number of layers will be okay. So, let me not say this quantity here, we will keep this as a variable as of now. Okay. Later on we will fix k. Okay. So, then we have, let us say, ORs and OR AND. So, we have some AND, okay, and then we have the leaves. Okay, for all these AND gates. So, we have constructed these. Now, what do we assign to these leaves? Okay. So, now consider this constant. So, let psi be the constant root 5 minus 1 by 2. How we get this root 5 minus 1 2 will be clear very soon. Actually, this comes from the root of a equation. So, with probability two psi minus 1, okay, assign value 1 to a leaf, and with the remaining probability. So, with probability 1 minus of 2 psi minus 1, which is nothing but 2 minus 2 psi, which is equal to 2 1 minus psi, assign a randomly chosen label from x1 to xn to the leaf. So, the construction is very simple. So, this is clear. Now, with probability this much, so I pick any leaf, with probability this much I assign it a 1, and with the remaining probability I pick any random variable from this set and I assign that variable to the leaf. Okay. So, this is the entire construction, and now what we will show is that so we'll see how we get that. So, that actually comes because of certain properties that we want. Okay. So, what we will show is that this formula that we have constructed with high probability, this formula will solve majority. Okay. So, that is what we will prove, or not even high probability, with non-zero probability. We will show that with positive probability the formula computes majority. So, if the formula computes majority with positive probability, it means that there exists some formula which computes majority, okay, and the probability is over this distribution. Okay. So, this distribution of assigning values to the leaves. Okay. So, now the entire thing is about the argument. How do we get this? Okay. So, any questions about the construction? Okay. So, now we will define, we will just need one definition here. We will define something called the amplification function. Okay. So, let me just see. So, let f of x1 to xn be a Boolean function. Okay. Then the amplification function of f comma af of p is defined as the probability that f of x1 up to xn takes a value 1. And what is this probability over? So, this is the probability over, so, or the other question also is that where does p occur? Okay. So, I haven't said what p is. So, p is the probability with which these variables take a value 1. Okay. So, where xi's are independent variables and probability that a xi takes a value 1 is p. The probability that it takes 0 is 1 minus p. Okay. So, this is the definition of amplification function of f. Okay. Now, in this context, we will just use a notation that let let a k p be the amplification function of an alternating tree with 2k levels, okay, as shown. Okay. So, essentially what I mean is that, well, A0 would be just the leaves, okay. A0 of any p would just be the value of the leaf. So, A0 of p is nothing but p itself. Then A1 of p would be whatever I am getting after the first OR. Okay. So, if I look at just 2 levels, what is the probability that I get at a node in level 2? A2 of p would what would be the value that I get at level 4, and so on. Okay. Now, we will try to estimate what this is, and we will try to give some properties. Okay. So, that is essentially what we want. Okay. So, the lemma that we want to prove is, and this is essentially will be enough to give us the theorem, is that for all k, a k p is monotonically increasing with fixed points 0, psi and 1, okay. And if 2k is greater than 5.3 log n, then a k of psi minus one minus psi of n is less than 2 to the power minus n, and a k of psi plus 1 minus psi over n is greater than 1 minus 2 to the power minus n. Okay. And we will show that once we are able to establish this lemma, the theorem is not very difficult to show. Okay. So, we have to show several things here. Firstly, that this is a monotonically increasing function, these are the fixed points of this function, and the function satisfies the property that if I take k to be bigger than 1.6 whatever 1.65 log n, then a k of this quantity is at most 2 to the power minus n, and a k of phi plus 1 psi plus 1 minus psi over n is greater than 1 minus 2 to the power minus n. Okay. Okay. So, let us see. So, how do we prove this? So, first of all, let us try to compute what A1 of p is. So, what is A1 of p? Okay. Let us look at this tree. Okay. So, what is the probability that this node, okay, outputs a 1? So, the probability that this node outputs a 1 is the probability that both these nodes must be 1, right. So, if both these nodes are 1, then this node outputs a 1. Okay. So, the probability that both these nodes are 1 is p over here. Okay. So, the probability that an AND gate outputs a 1 is p square. Now, what is the probability that an OR gate sitting over here outputs a 1? So, the probability that an OR gate outputs, so when does a OR gate output a 0. So, it will output a 0 if both these guys output a 0. So, the probability of that happening is 1 minus p square, right, whole square, because the probability that one AND gate outputs a 0 is 1 minus p square, probability of both of them outputting a 0 is 1 minus p square whole square. And so, the probability that an OR gate outputs a 0 is equal to this. So, the probability that the OR gate outputs a 1 is 1 minus this quantity. Okay. So, this is essentially what A1 is, because this is the 2k levels. So, we can simplify this, and this turns out to be 2 p square minus p to the power 4. Okay. Now, this is A1p. Okay. We will also be looking at, we need to understand the, like, when does the function increase, how does the function behave. Okay. So, to understand how does the function behave, we will look at also the derivative of this function. Okay. So, what is the first derivative of this function? The first derivative of this function is 4p minus 4p cube. So, I will write it as p minus p cube. Now, what is a k of p? How can we define a k of p? How do you define a2 of p? So, a1 of p is basically the probability over here, a2 will be after 2 more layers, but how does that computation happen? It will happen in the same way, right, because instead of p, now I will have a1 of p that I am taking for those 4 nodes, and the same way I compute a2 of p. So, in general a k of p will be a1 of the quantity a k minus 1 of p. Okay. So, this can be defined recursively in terms of a k minus 1. So, the derivative of this will be a prime or okay, fine, a prime of a k minus 1 p times a prime k minus 1 p, right. So, this is the derivative. Now, let us try to study how does the what are the fixed points of this function. So, what are the fixed points of this function? To study the fixed points, it must be that now, note that whatever are the fixed points of A1p, those must also be the fixed points of all AKP, because let us say if I have a fixed point of A1p, that is basically a point p such that A1p is equal to p. So, again if I substitute, let us say A1p for p over here, for A2 also I get the same fixed point, for A3 also I will get the same fixed point, in general for any k I will get the same fixed point. Okay. So, the fixed points are the same over here by the definition of AK. Now, what is the fixed point? So, 2 p square minus p to the power 4 equal to p. So, if we solve this, what do we get? What are the fixed points? So, 1 is very obvious, 0 is a fixed point. Anything else? Any other obvious fixed points here? So, if you take p equal to 1, on the left hand side you get 2 minus 1 is 1, on the right hand side also you get a 1. So, 1 is also a fixed point. So, if I take 0 and 1 as fixed points, so what I get is that I will get the equation. So, 0 and 1 are fixed points. So, if I factor out p and p minus 1, what I will get is okay, let me, I do not have it over here. So, I will get something like p square plus p minus 1 equal to 0, and the roots of this equation will be p is equal to minus 1 plus minus root over 4 plus 1 over 2, which is equal to root 5 minus 1 over 2. Well, root 5 minus root 5 is not considered because p is a probability. So, it has to lie between 0 and 1. Okay. So, this value, the minus I mean the negative value of p is ruled out. So, this is the only other fixed point. Okay. So, the graph of this function will be as follows. So, it will look something like this. Okay. So, this is a fixed point. So, at 0 I have a fixed point, at 1 I have a fixed point, and then somewhere in the middle, not in the middle, at this value, and now note that this is nothing but our psi. Okay. So, that is the reason why we had chosen this particular psi over here. We have another fixed point. Okay. So, this shows that these are the fixed points and the function is monotonically increasing as well. So, because A1 is monotonically increasing, all the AKs can be shown to be monotonically increasing as well. Okay. So, now what we have to prove is that AK of psi minus 1 over psi. In fact, what we will show is we will show only one of the inequalities, the other kind of is just follows by symmetric argument. So, I just factor out x minus 1. So, 1 is a fixed point. So, I first of all I factor out p because 0 is a fixed point. So, 0 is here. So, I get 2 p minus p cube equal to 1. So, in this equation I factor out x minus 1 because 1 is also a fixed point. So, then I get p square plus p minus 1. Okay. I mean you can verify that p square plus p minus 1 into p minus 1 into p will give you this.
We need the 4 roots basically.
Huh?
We need the 4 roots.
No, not 4 roots, we need only 3 roots because as I said that the 4th root is negative. So, that that does not occur. Okay. Okay. So, next what do we have? So, we have the fixed points, we have A1. Now, let us try to see how the derivative of this function behaves, sorry, how this derivative behaves. So, what is the structure of this derivative? So, let us look at this. So, this is equal to 4 p minus p cube. How does this look like? Okay. So, let us see what is the maxima and minima of this. So, to find maxima or minima, let us look at the double derivative. So, a double a prime prime p will be equal to 4 1 minus 3 p square, and if I equate this to 0, I get that 1 minus 3 p square equal to 0 implies p is equal to 1 over root 3. Once again minus 1 over root 3 is not needed for us. So, this is a extremum point. Okay. And you can again check that this is actually a maxima as well. Okay. So, we will call this as phi, this point. So, essentially how the graph looks like is between 0 and 1 is, so it will have a structure like this. So, this is the graph of A1 prime P. Okay. So, once again this has at 0 and 1 this takes a value 0, okay, and at phi it takes the maximum value something. Okay. And you can again check that psi is actually a quantity that is greater. Okay. So, if you just check, so this I think turns out to be something like 0.58 or something, and psi is something like 0.62. Okay. So, it is slightly greater. Okay. Now, the reason why I am looking at psi and the reason why I am comparing these two constant is because I actually need to look at the behavior of this function when the argument is slightly smaller than psi and when it is slightly larger than psi. Okay. So, what happens to this function around psi? So, as I said that we will only look at one side. Okay. So, we will let us say we will look at only one side, we will look at the place, we will look at the case when the argument is less than psi over here. Okay. So, I think we have all that we need. Okay. So, one more property that I want to show is what happens to the derivative when the argument is psi. Okay. That is basically at this point what is the value that the function takes. Okay. So, let us substitute. So, we have 4 psi minus psi cube. So, that is 4 psi 1 minus psi square, but what is 1 minus psi square? Huh? Why is it psi? From this equation, right. So, it is a fixed point. So, 1 minus psi square is nothing but psi. So, I get 4 psi square. So, this is nothing but 2 psi whole square. Okay. Okay. So, now I will write down 2 claims and that will show us the lemma.